Okay, in the previous video we looked at permutations, defined what a permutation was, and we developed a formula for permutations and also found that permutation feature on our calculators. So a quick recap, remember a permutation is just a fundamental counting principle in disguise. That's all that it is. And as a result, there's two things you got to keep in mind when you're using the fundamental counting principle to count permutations is that you can't repeat. So there's no repetition. And count order. And that's actually built into the fundamental counting principle. When you're using the fundamental counting principle, whether you're aware of it or not, you are actually keeping track of order and counting every item where the order happens to be different. And we'll illustrate that better in a few seconds with an example. Now, combinations, which is kind of the focus of this video, as is still based on the fundamental counting principle. We still can't have repetition. So permutations and combinations, beware there's no repetition in either of those. And as you probably can guess, it's got to be something different about combinations and permutations. Yeah, we do not count order. So make sure you don't overcount combinations by making sure you remove order somehow. And let's illustrate. We'll take the letters A, B, C, D, and E. And we're going to create a three-letter. Sorry, not three-letter. That'll be way too time-consuming. Let's do two-letter permutations. And once we have those sitting in front of us, we can easily adjust that to get our two-letter combinations in a few more moments. So let's count them first. How many two-letter permutations would there be using these 5 letters? Well, there's only 2 selections that we're making. Via the fundamental counting principle, we could choose any of the 5 letters in the first choice. We can't repeat, so we have to drop down to 4 for the second choice. So there must be 20 two-letter permutations. So let's try to list those. Where will we put them? Maybe we'll stick them right here in this empty space. So this is going to get a little time consuming here, but let's just be cyclical about it. We'll start with A, and then I'll cycle through the remaining letters. So we can have A, B, A, C, and D, and E. So essentially I'm just doing a tree diagram here without the tree. If you're having problems, go ahead and use a tree diagram. So I'm going to keep in mind I can reverse the order of those letters, so I'll leave a space, and I'm going to go now to B as my first choice. So it'll be like the second part of our tree diagram, and then of course the second choice will be the remaining letters, so BC, BD, and BE, and I can reverse those letters in a few more seconds. We'll go to C, and then if I pick C, I have D or E remaining, and then finally the last pair of letters, adjacent letters, D and E. Okay, now keep in mind I don't have any AAs or BBs, repeated letters in there, because we're not allowed repetition with either one of these things, permutations or combinations. So let's do some reversal now, because if you notice we count these up. I got 4, 5, 6, 7, 8, 9, 10. I'm missing half of my permutations, and that's a pretty easy fix as long as we just reverse each of those letters. So my first column there, we'll reverse each of those. And we can get our 20 permutations and reverse this column. There'll be CB, DB, and EB. DC, EC, and finally ED. Now there's nothing glamorous there, but of course it's a good idea to have them all sitting in front of us so we can clearly see that if I just want combinations, I only want to count whichever column I want to take, or one of those first 2 columns. We'll do the first one because that's of course the one we wrote down first. I don't want to have to reverse all the letters. I do need to keep that in mind if I'm counting order for permutations though, of course. So the whole block of those numbers, all 20 are the permutations, and if I want the combinations, I want precisely half of those. So we know right now that there should be 10 2-letter combinations. just by looking at all the permutations listed. Okay, so how can we get half of those? Well, of course, we just need to divide 20 by 2. But the question is, why are we dividing by 2? Well, the hint is sitting right here. How many ways can I arrange A and B? Well, since there's 2 letters, there's 2 factorial ways we can arrange A and B, or A and C, or A and D, or any of those 10 combinations. So we're actually dividing by 2 factorial, which might not be immediately obvious, but to generalize this process, you have to divide by the size of the permutation that you actually set up to get the correct number of, in this case, the same size 2-letter combinations. So there's actually 10 of these. That's what we're looking for, and they're listed there. So now let's look to see how we can do this with our permutation formula and make an adjustment to that to get our combination formula. Get rid of that. So if you recall in the last video, there's a general formula for permutations, just usually written something like that with an N and an R. And if you're choosing from N items, a smaller subset, or the same size, remember it's not a proper subset, it's any subset, and can actually be the same size. You could take all 5 things, but in this case we're only taking 2, so it is a actual proper subset. But anyway, let's focus on our formula. We don't need to go back to set theory from the last chapter. It's going to be n factorial over the difference in those 2 letters, n minus r factorial. So in this situation, we have 5 letters, and from that set of 5, we're taking subsets of size 2. So our permutation formula tells us that we need to take 5 factorial and divide by the difference, which of course is 3 factorial. And it might not be obvious, but what that's producing is 5, 4, 3, 2, 1, all over 3, 2, 1. And what I was saying about what's not immediately obvious, that's actually just producing our fundamental counting principle, because all those numbers in the bottom divide into those numbers repeated on the top, and lo and behold, we see all we end up with here is 5 times 4, which we got a few moments ago using the fundamental counting principle. So this permutation formula works. It's not really that useful because, of course, you're probably better off using the fundamental counting principle. It's easy to memorize. But what we now can do is take that NPR formula, and I think we'll stick with the specific case here. If I want specific case. Get rid of that. If I want 5 C2, that, of course, is the number of 2-letter combinations taken from these 5 letters, A, B, C, D, and E. It's actually just the permutations that we counted divided by 2 factorial. And, of course, that second 2 factorial comes from that second number in our combination. That's the size of our permutation that we need to divide by that factorial to get rid of all that order that we don't want to count for a combination. Okay, so let's actually look at that one more step, maybe back in white here. So if I set this 5 factorial up again, actually let's go back to red. If I set up my permutation formula and not the reduced canceled one, the 5 factorial over the 3 factorial, we realize that if I'm dividing that by an additional 2 factorial, that little 2 factorial shows up on the bottom, and that's what's removing. We'll say removes the order from the permutations. And we'll just abbreviate that, obviously. Okay, so we can set up now a formula for combinations. A little bit more space to wrap up. There. So we'll stick to white, I guess, which is our combination color in this case. So what if we do NCR? It's going to be n factorial on the top. Remember, this is identical to our permutation formula. We have an n minus r on the bottom, which is the difference in those two things, obviously. And then, most importantly, we have the whatever the size of those subsets are, we have to divide by that subset factorial, size of that subset factorial, to again remove our order. And there is our combination formula. So we're going to just wrap up by going to our calculator, type in 5C2, and maybe we'll type in 5P2 as well, and of course recognize that we can get that information most of the time from our calculator, but I think it's still good to know what the combination formula looks like and try to demystify it a little bit as well. Okay, so let's go back and we'll go 5P2. There's in my probability menu here, and these are our permutations. So 2 letter permutations from 5 distinct letters is 20. If I go 5 P2, of course we'll get exactly half of that, which is 10. So if you're wondering where those what your calculator is doing, of course it's using both the permutation formula, as you see here, and the combination formula that you see there as well. And also, as we wrap up here, keep in mind combinations will always be smaller than permutations, right? Unless, of course, you're taking maybe 0 items, but we won't get into any of those weird situations. But if you're taking two letters from 5, of course, you're going to have more flexibility, more options when you count order than when you don't count order. So get that notion in your head and expect almost all the time for combinations to have a smaller number than the same size permutation. So there we go. There's your overview of a comparison between permutations and combinations. And at this point, just know where those buttons are in your calculator. And in subsequent videos, we'll focus on how do we know which we should be using. When do we use permutations and when do we use combinations? And that will make a little bit more sense in specific contexts.